Hi, everyone. Thank you for joining us. I'm Danielle Gauthier, Senior Product Marketing Manager for Threat Intelligence at Dragos. Welcome to our briefing on the FrostyGoop ICS malware. So let me introduce our expert speakers today. We're joined by Kyle O'Meara, Carolyn Allers, and Matt Paul from the Dragos Threat Intelligence team. We have much to cover, and we're really glad you could join us. But before we get started, this session is being recorded, and the recording and the slides will be emailed to everyone within 2 business days. Also, your microphones have been muted, but we still want to interact with you. Please use the Q&A chat feature to submit any questions you have, and we'll try to get to your questions at the end. For today's agenda, we will share some background information, followed by our analysis of the FrostyGoop ICS malware. Then we'll discuss an incident where FrostyGoop was deployed in the wild and share some research on the threat landscape. Finally, we will walk through our process for transforming intel into detections, and we'll close our briefing with some recommendations, followed by questions and answers from you. And now I'm going to pass it off to our panel of experts.
Thanks, Danielle. Hello, I'm Kyle. At Dragos, we define software to be ICS malware. It has 2 requirements that need to be fulfilled. It must show ICS knowledge and that it can communicate with OT-specific protocols or interact with OT equipment through non-standard means, as well as must have intent of the creator or the user that indicates a desire to cause harm, typically disruption or destruction within the OT environment. We regard FrostyGoop as the 9th ICS malware, but more importantly, the first one that used Modbus to cause effects against ICS devices. We've seen others that have scanned or enumerated, but not directly interacted or facilitated with malicious intent. So let's take a look at the attack that happened. So, that takes a lot of assessing. It goes into the knowledge of what's being done with the tooling, how things were accomplished, and then basically deriving your assessments on that knowledge is around the software, itself and what happened during the attack. So this specific attack, we Dragos were made aware of attack that occurred in Ukraine in January 2024. The Ukrainians SBU shared some further technical details with us on this event. The technical details shared that it disrupted a district heating facility during sub-zero temperatures that resulted in the loss of heating to over 600 apartment buildings. And it took around 48 hours for full, complete remediation to occur. So during this time, we assessed that this incident was facilitated by what we call FrostyGoop. Based on our analysis of the malware and the other artifacts uncovered alongside of it, we assessed prior to this attack, FrostyGoop was used to target controllers on the internet that had Modbus ports opened.
Hi, I'm Carolyn. I'm going to be going over the FrostyGoop malware capabilities. This malware can accept optional command line arguments, separate configuration files to communicate with victim devices. It communicates with ICS devices over Modbus TCP port 502 to send Modbus commands to read or modify data on ICS devices. It also has an option to log output to a separate JSON configuration file or separate JSON file or a Windows console. A little bit about the Modbus TCP protocol. It was created by a company called Modicon in 1979, initially developed for Modicon PLCs and industrial automation systems, but now is an industry standard method used worldwide. It's used for transferring data between industrial control devices like PLCs, DCSs, controllers, sensors, actuators, and it uses a client-server approach where the client, such as an HMI, can send requests like read and write to servers like PLCs. Modbus has been targeted by researchers for many years. It's everywhere. Its attack surface is huge, and it has several issues due to its lack of security. I mean, Metasploit even has a Modbus module in it. There's a lot of information on the internet about Modbus. Making something like FrostyGoop would not be difficult. We found multiple samples of FrostyGoop malware, most of them named modbus.exe. The malware is written in Golang, which is pretty uncommon, especially in the OT environment. It's an easy to use language, small disk presence, statically compiled. And this malware used open source libraries for the Modbus functionality. The repo they used was publicly available on GitHub, and they even had whole examples on how to use Modbus in that GitHub repository, making it super easy for these malware authors to use Modbus protocol. It just goes to show that malware authors are using what's available as they do in the IT space. They just use publicly available libraries, import them into their malware so they don't have to go rewrite the protocol itself. We saw this in other OT malware like Pipe Dream and Crash Override and Cosmic Energy as well. FrostyGoop functionality. Information required to initiate a TCP connection with a victim device and send Modbus commands to the device can be specified in two ways. One being through command line arguments and another being through a JSON configuration file. I'm going to go through how it uses command line arguments to connect to a victim device first. This is an example of the command line that would be executed. First, in blue, we have the name of the FrostyGoop malware, modbus.exe, followed by the target device IP address. And then in green would be a mode switch for read, write, or write M. Read being Modbus command code 3, read holding registers. Write command code 6 to write to a single holding register, or write M command code 16 to write to multiple holding registers. Following that, in red, there's the address, which would be the Modbus register address on the target device, and count, which count would be used for read and write M to specify sequential Modbus register addresses following the address specified. And then there's another option, output log.json. So that was just to log all the output to a separate JSON file. The other option would be to include all the victim information and command codes and Modbus register addresses in a separate JSON config file. The command line execution would just be name of the FrostyGoop sample with input task to specify the JSON configuration file name. The FrostyGoop sample would read in that config file that should contain the victim IP address, those command codes 3, 6, or 16, the Modbus register addresses, count if it's going to have it read or write to multiple registers, and a value if it's writing. There's actually two different configuration files that FrostyGoop accepts, one of them being the one I just talked about with victim device information for connecting, and the other one would be to specify a time to begin Modbus TCP communications and various times to delay sending Modbus commands. Both of these are optional. This is just a quick overview of the Modbus network traffic between FrostyGoop and a victim device. FrostyGoop connects to the target IP address over Modbus TCP port 502. FrostyGoop starts sending the Modbus commands to the device responds, and then FrostyGoop closes the connection and exits execution. As far as the logging capabilities, it can log to a Windows console that it starts up when FrostyGoop starts executing, It logs the IP address of the victim device it's connecting to, the Modbus register it's sending commands to, as well as a plus and minus after it's sent and received communications. The plus sign on there would be on success of the command. So the malware sends a read, the device responds correctly. It would log a plus sign and it's a window console. It would log a minus sign if the response from the device contains something like an exception. An example might be when like if a holding register does not exist on that device, an exception would be sent back to the malware and the malware would log a minus sign in the Windows console. The other logging is that JSON file. If that command line option was used, it would log all that same information into a separate JSON file that's saved. We did find a sample of the configuration file containing an IP address and some Modbus commands in it. The name of the file was tasktest.json. The IP address in the sample configuration file belonged to an encode control device, which are typically used to monitor sensor parameters like temperature, pressure, and insulation for process control and district heating, hot water, and ventilation systems. While we did find this and we assessed that adversaries were using FrostyGoop for testing purposes against encode control devices, but FrostyGoop is not specific to encode devices. The Modbus functionality is very generic to Modbus TCP, so it can connect to anything using Modbus TCP.
Thanks, Carolyn. So, as Carolyn mentioned, FrostyGoop can be used against all Modbus targets. So here's a theoretical attack, right? Very simplistically, you can just scan the internet for any publicly available Modbus devices, pick your target. You can use the command line feature of FrostyGoop, or you can compile into the JSON config as Carolyn described earlier, launch your attack, and then rinse and repeat. It's very simplistic. So let's look at the timeline itself of the attack timeline. So during the investigation of the attack, a discovery was made that the adversaries possibly gained access to the victim network around April 2023 by exploiting a vulnerability that has not been determined in an externally facing MikroTik router. Between the 20th and 26th of April of 2023, the adversaries deployed a web shell with a tunnel capabilities similar to Regorge, an open source web shell tool, which allowed them, which accessed predominantly via Tor IP addresses. Then there was a 6-month lull in between there. There could be a lot of hypothesis of why there was a 6-month lull, whether they could be testing the tool, whether they can be building a tool. It's undetermined. You can make your own assessments and your hypothesis is what went on during that 6-month lull time before FrostyGoop itself was uploaded to a public malware repository. The investigation obviously also revealed around in November of 2023, and then in late November of 2023 and about mid-December of 2023, the adversaries collected the registry, the SAM file registry hive, which contained user credentials for the system. And then it was in January, near late January, where the adversaries initiated a layer 2 tunneling protocol connection to 2 Moscow-based IP addresses to then launch their attack. So kind of going on the attack timeline. So the adversaries, what they did was they downgraded the firmware on the controllers from version 51 or 52 to 50. This 50 version of the controllers lacks monitoring capabilities that were employed at the victim facility, resulting in a loss of view. The adversaries did not attempt to destroy the controllers. Instead, the adversaries caused the controllers report inaccurate measurements, resulting in incorrect operation of the system and the loss of heating to customers, i.e., the heat regulation systems were impacted. So let's look at, what's out there, what's sort of the threat landscape of what exists, right? So these are rough estimates. These numbers almost change daily. So there's roughly 46,000 exposed ICS devices communicating over a Modbus, and roughly about 100 or so, if more, encode devices that are also exposed to the internet. We assess with some, confidence that the number doesn't, accurately represent what the exact number of exposed encode controllers out there. Could be higher, could be lower. Same thing with Modbus devices, right? This changes daily. Gets removed from the internet, what doesn't. So then we look at this, from the initial attack vector, what's going on here. So, as I described, as was shared with us, that the initial attack vector was perimeter devices. So this isn't just something that's exploited by the threat group behind FrostyGoop, right? All different types of threat groups target perimeter devices, from VoltSite to CamaSite. We see a lot of hacktivist groups doing this, from the Cyber Avengers to the Cyber Army of Russia. There's a plethora of ransomware and cyber criminal groups that do this. So, it's important to keep perimeter devices updated to the latest security patches, right? Especially when there's known proof of concepts that sit on the internet, and that can be easily used. And these adversaries don't need to actually develop their own tooling. So shifting gears to what can be done, some recommendations. So these are some in the context of FrostyGoop. We highlight some of the things here. Let's not have Modbus devices accessible to the internet, especially if they're, OT specific systems that are connected right to your OT environments. It's important to have visibility. You can't defend against what you can't see. So having some type of monitoring in your OT environments is hugely important. Network segregation is also important, controlling what can be seen and at least privileges, and allowing not the adversary to move laterally through your network, and what can be, understanding that, if you have a flat network, the adversary can get from one avenue to the other. In certain cases, we always try to enforce multi-factor authentication. And specifically in this case, monitoring traffic to your port 502 Modbus devices is also helpful. And patching can be difficult in OT environments, but it's important to think about the next never approach to patching in the OT environment, and having some type of patching priority list. And obviously creating a secure architecture, to help secure environment is a sort of a tactical way of really getting ahead of this and helping prevent certain similar situations to, this sort of attack.
Thanks, Kyle. This is Matt. I'm a detection engineer here at Dragos. It's my job to take the threat intelligence and the background information and the commands that are displayed in telemetry, which is over the network that Kyle and Carolyn and folks like them produce, and turn those into detections for the Dragos platform. Here's kind of like the timeline of our work on FrostyGoop. Analysis kind of started in earnest in May of 2024. Along with that analysis, I was helping and starting to look at, working with the team to start to look at the way FrostyGoop manifests itself on the network. We had a breakthrough coming through in July, and we were able to kind of see, based upon the way FrostyGoop was coded, that it delivers sort of a tell, if you will, on the network in terms of its telemetry. And utilizing this, I don't want to say like this one simple trick, it allowed us to differentiate FrostyGoop from normal Modbus TCP commands. We were able to write a very robust detection for the Dragos platform. So in addition to other detections, which we already have, which I'll talk about in a moment, we have a definitive FrostyGoop detection, which allows us to alert on telemetry produced by FrostyGoop itself if it's seen on the network through our sensor. So, I talked about detections for a moment. There's actually different types of detections, and I'll talk about those, just, give some examples. the four types of detections that we have are, and probably most places have, are indicators, configuration, modeling, and threat behavior. And if I was to give examples of those, an indicator detection is basically something happened, right? So this thing happened. It may be bad, it may be good. You just want to know about it. And it's a pretty simple type of detection, and those are indicator detections. Configuration detections apply to whenever a configuration changes. So if you go in and you were to update a configuration of a system, we would write a detection around that to let the operators know this configuration changed. A modeling detection, that detects baseline. So we know the way something is supposed to look, or perhaps an operator has configured the way something is supposed to look. And if the environment or activity deviates from that baseline, the modeling detection will pick that up. And then with threat behavior detection are detections which are really indicators that somebody somewhere is trying to do something bad to your system. And the threat behavior detections can consist of indicator, configuration, and modeling detections, or many of those together. But the key point there is the intention behind the detection and the intention behind the activity. These four types of detections are broadly composed of two different types, atomic and composite detections. So any of these indicator, configuration, modeling, and threat behavior can be atomic or composite detections. Indicators are generally atomic detections, but they don't have to be. And atomic detections are basically composed of just one piece of evidence, one bit of telemetry, or one bit of evidence that comes from a system. And composite detections combine multiple atomic detections, two or more, in order to give more of a robust and higher fidelity signal about the activity in the environment. And where do we get this telemetry from? Primarily from network monitoring, which is things that are happening on the network. We get those from our sensor, and host logs, specifically for Windows hosts and some other hosts as well. These detections, all of these factors are combined into a robust detection catalog, which are then codified into the Dragos platform, so that it's basically taking the intelligence that folks like Kyle and Carolyn produce, codifying that into the platform, and then when you get a notification, it'll alert basically on all of the intelligence work that we've done. So these were some of the detections when FrostyGoop was first announced that were out there. This does not yet include the purpose-made detection that we made specifically for the telemetry. But if you look toward the bottom of this table, that's really kind of the most applicable detections. As Kyle outlined, the attack occurred from external devices. The Dragos platform at that time would have alerted the customer that, hey, there's an external device now communicating in Modbus TCP with your device. They're writing to your devices, and you've never seen this before. So immediately you will get the picture that something amiss is going on. And I often hear attackers say something like, well, I have to be right, I only need to be right once, and defenders only need to be right, have to be right 100% of the time. I don't personally subscribe to that. And the reason being is there are many steps along the way, and almost everything has to go right for the attack to go off without being detected or successfully. And a good detection anywhere along those steps, if it alerts a defender and that defender gets curious about the detection, especially if the detection is of high enough fidelity and high enough severity, as soon as that defender starts pulling that thread, all it takes is one good detection to unravel months, maybe a year of effort by attackers. And so these were some of the detections that we already had in place. And then we were able to look at the telemetry as mentioned and create a purpose-built detection. So this would be the notification you would receive in the Dragos platform for this purpose-built detection. You can see it describes which asset is communicating to which other asset. The telemetry, I'm not going to go into full detail regarding what differentiated the FrostyGoop telemetry, but it's suffice to say that the authors of the malware introduced some artifacts or byproducts of the way that they coded the malware, which allows us to very easily differentiate it from what would be normal. And so what we were able to do is we saw that, working with Carolyn, we saw that. We then took dozens and dozens of legitimate packet captures for legitimate Modbus TCP traffic. And then we took some FrostyGoop created packet captures, and we put all of those into basically about 200 lines of custom-made Python code to test the hypothesis that, okay, this is what we think we're seeing with our eyeball, let's now test this programmatically. And over all of those tests, it was proved out that we were able to detect this in packet capture. So we then were able to parlay that into this very high fidelity detection, which the turnaround time from the discovery basically of this these artifacts or this telemetry, the way that they're communicating to the detection publishing was just a matter of days. So, and that's going out in the very next KP release, the knowledge pack release. Next slide, please. And so it's not just enough to have the detection. Okay, you get this detection, it fires in your environment. What do? Well, we've also written a very lengthy playbook that goes along with the detection. It cites the reports that reference FrostyGoop behavior. It tells you what FrostyGoop is. But most importantly, it tells you, okay, what do you do next? So the very first thing you'd want to do is this a false positive? It's not likely, but if it is a false positive, how do you rule that out with using other elements of the Dragos platform? It walks you step by step on how to rule those out. Additionally, if you don't rule out the false positive using the step-by-step methodology in the playbook, it then tells you or instructs a practitioner to how to go and find all of the behavior that would match the FrostyGoop behavior by utilizing the Dragos platform. And so that's very useful too. So first, if you can't rule it out, let's find the extent or the breadth. Let's put a bracket on where this behavior is. It'll instruct users how to take a packet capture to basically, if the behavior is still going on, how to get more evidence from this, more telemetry. And this will help investigators. And heaven forbid, if it can't be ruled out, and there are other notifications around the device, which are, which I showed a little bit ago, other detections, then it instructs security practitioners on how to elevate basically the scenario to an incident response scenario. So it's a very robust playbook, and our high severity detections, almost all of them are coming with playbooks at this point in time. We're writing playbooks for every single one. So I think that's it for the FrostyGoop detection. And I think we're going to go to Q&A with Danielle. Thank you.
Thanks very much for sharing your insights. Time to take a few questions, so feel free to pop your questions into the Q&A. I've seen a number of those coming through. So the first question I think is for Carolyn. And we've gotten this question a few times actually, how did we come up with the FrostyGoop name? Where did that come from?
Because bad guys don't deserve cool malware names.
Thanks, Carolyn. Kyle, I have one for you. Is Dragos tracking a specific threat group behind this attack?
So currently, we have internal tracking that we call temporary activity threads. Right now, this is just one temporary activity thread that we're associating with this adversary. We haven't seen them do similar attacks yet. We're tracking this, other activity that could be surrounding this, and it could evolve where it could fall into one of our current threat groups or could evolve into its own threat group as a whole as Drago tracks it. But currently, a short answer is no. We're just tracking it as an internal, temporary activity thread.
Kyle, I have another question for you, Carolyn. And I think you answered this, but good to reiterate it. Could this be used against devices other than ENCO control devices?
Yeah, the functionality is very generic to Modbus TCP.
Okay. Okay, Matt, I've got one for you. Can you show us what the packet capture looks like? Is it typical? Is it like a typical MB-TCP packet?
So the commands are typical, but things are adjacent to those commands, which are not necessarily typical. And so FrostyGoop as a whole, it's not just the commands, it's other things that it's doing in addition to the commands. I can't show the packet capture at this time, but it's not FrostyGoop doesn't present itself entirely as regular Modbus TCP, a Modbus TCP session.
Thanks. Carolyn, did you find any C2 or callback functionality on the FrostyGoop binary, or is it does it pretty much work just as Modbus command level interface?
No, there wasn't any C2 or callback functionality. It just has that Modbus functionality functionality to connect to devices and send Modbus requests.
To piggyback off on that, it's the C2 that we were made aware of was set up on the compromised router itself through a tunneling protocol.
Kyle, can you talk to what changes the adversary made on the targeted controllers, which resulted in the heat being turned off for 2 days?
Yes, I saw that question come in and I figured we'd answer it live. Yeah, so specifically what we were shared, the information that was shared is that they downgrade the version of the controllers from whether they're running 51 or 52 to a version 50. And this version lacked the monitoring capabilities that were employed at the victim site. So because of the downgrading of the version, there was no monitoring, and that when FrostyGoop was executed, allowed the adversary to cause the controllers to report inaccurate measurements.
Thanks, Kyle. One for you, Matt. How exactly do you detect FrostyGoop? What is the exact indicator? It seems like this malware actually looks like a regular Modbus client, and implementations of such clients are plentiful, and it's easy to write new ones. So can you
So that's a good observation, and we thought the same at first. This looks just like Modbus TCP. So how are we even going to detect this? But then basically, as we were able to, with Carolyn's help, go into the code and then replicate what FrostyGoop is doing on the wire, quickly, well, I wouldn't say quickly, a theory quickly emerged, and then programmatically we were able to go through multiple iterations to show that there's enough of a deviation or a handhold. I can't go into the specifics of that deviation, but there's enough of a deviation in the handhold in the way FrostyGoop communicates compared to a legitimate device that allows us to alert on it with a very high fidelity.
Thanks, Matt. I have another question for you, actually. Regardless of the additional development and analysis you did for custom signatures, what out-of-the-box capabilities does Dragos have to detect and alert this type of activity?
So the real ones that would have real out-of-the-box capabilities were the ones I kind of alluded to at the bottom of the table a few slides ago, which were something new is talking to your device from an external IP address that you've never seen before, and it's talking in a way you haven't seen before. It's legitimate. The communication may be legitimate commands, but there are several indicators there that it's new, never seen before. And if things shouldn't be talking to your devices from an external network, that would have fired as well, which would have let you know. Any one of those probably might have been enough to alert a security practitioner, hey, I should dig into this. And with the Dragos platform, they can then pivot directly to kind of look at the ID if they can get it of what's talking to your device. So
Thanks. Okay, I think we answered a number of questions directly in the Q&A, and just based off what I'm seeing here, I think that's probably all the questions that we're going to be able to answer right now. If you do have additional questions that you do want to, discuss with us, please do reach out. So thank you everyone for your time today. I really want to thank our speakers. We hope the information we've shared was helpful. And if you have additional questions or concerns, we encourage you to reach out and we can connect you with the answers and help you need. And thanks again for all you do to protect the world's critical infrastructure from cyber threats, and have a great day.